Hello and welcome to Real Analysis Part 25. And first I want to thank all the nice supporters on Steady or PayPal. In this video today we will talk about the uniform convergence of a sequence of functions. In order to understand this, please first recall that we call a sequence of functions pointwisely convergent to another function f if for all points x tilde we have the convergence of the values at this point. This means that in this formulation with the quantifiers, you are allowed to choose different capital N's depending on x tilde. And indeed, this is the only thing we will change to get the uniform convergence. So we call a sequence of functions uniformly convergent to f if for all epsilon greater than 0, there exists a capital N such that for all indices n greater or equal than n, and for all points x tilde in I, we have that the distance between the values is less than epsilon. So you see, this quantifier from before is pushed to the right. Of course, therefore this looks similar, but now this capital N works uniformly for all points x tilde. Of course, therefore this looks similarly, but now this capital N here works uniformly for all points x tilde in I. That's different from before, because here you could choose capital N depending on x tilde. So there could be different capital N's here. However, for the uniform convergence, this N here has to work for all x tilde at the same time. And exactly this is the reason we call it the uniform convergence. And please keep in mind, this new order for the quantifiers changes a lot. Let's visualize that in a picture. So here you see the graph of the function f, which is our limit function. Now if we fix one point x tilde on the x-axis, this inequality here tells us that the value fn x tilde lies somewhere in this region. So we have our epsilon here and here. However, we also know this inequality here should hold for all x tilde. Hence we have to move this region here through all the points. In other words, what we get is such an epsilon tube around the graph of the function f. So the graph of the function fn needs to lie inside this epsilon tube. And of course also the graphs of the functions in the sequence that come after this capital N. This is exactly what the uniform convergence tells us. So you immediately see this is more than we had for the pointwise convergence. And also this picture tells us that it should be possible to measure a distance between two functions. By having this distance you can see that the uniform convergence is indeed very natural. For this we first should look at a picture again. Let's take two functions and their graphs. Now the question is, how can we measure a suitable distance between both functions, or in other words, when would you say that the functions are close to each other? Of course, what you already know is that for each point x tilde we can measure the distance of the values. So what you have to calculate is the absolute value as before. So if we call the point just x, we have f of x minus g of x and then the absolute value. And of course, as before, we could do that for all the points x from the domain I. There you see, we find small distances, but also larger ones. And indeed, the largest one we would find if we take the maximum of these numbers here. However, because we don't know if the maximum really exists, we should take the supremum. Hence, this number here tells us, in fact, how close the two graphs are. So we have a distance measure for two functions. And usually we just call it the supremum norm. The common short notation for this would be two bars left and right, and the infinity symbol as an index. And then we have f minus g inside. So this is the supremum norm of f minus g. Now as promised, with this we can rewrite the uniform convergence definition. It simply means that the supremum norm gives us a sequence that goes to 0. So fn minus the limit function f measured in the supremum norm goes to 0 when n goes to infinity. So we started with a sequence of functions, but what we got here is an ordinary sequence of numbers. Therefore, this is also the ordinary convergence for a sequence of real numbers. Okay, now after all these definitions, let's look at an example. So maybe we should take one we already discussed in the last video. There we had some simple functions that got steeper and steeper here until the pointwise limit was this function. We want to calculate a little bit, therefore let's say this value here is -1 and the one above is 1. What we will see now is that we have the pointwise convergence, but not the uniform convergence. Therefore, what we should look at is the distance between Fn and f in the supremum norm. Indeed, this is what we can immediately calculate when we look at the jump. So here we have the jump of our limit function f. Now it does not matter which of the functions from our sequence we choose, because all of them are connected from bottom to top. Hence you can always just take the middle point here and measure the distance to the limit function, which is by our given values here always 1. Hence we don't need to calculate anything, we immediately know this supremum norm is always greater or equal than 1. And we don't need anything more because we immediately know we can't have this convergence to 0, because this distance does not get smaller than 1. Now this simple example, without much calculation, directly gives us the following result. Having the pointwise convergence does not tell us that we also have the uniform convergence. However, it's also a nice result and not hard to show that we have the other implication. Hence the uniform convergence is indeed stronger than the pointwise convergence. And for us, the uniform convergence will be very important later because it conserves nice properties of functions. For example, it conserves continuity we will define later. That's something that just the pointwise convergence can't do. However, one property you already know is the boundedness of functions. And the uniform convergence also conserves this property. This means if you have a sequence of bounded functions and they converge uniformly, then the limit function is also bounded. Okay, all details about these properties we will discuss in the next videos. Therefore, I hope I see you there and have a nice day. Bye.